Hey guys, how's it going today? Happy Thursday. Alright, we've got some work to do. We're going to talk about Project 1. I'll go over my solution to the maze solver, and then we'll get into stacks and queues. Let's see. Alright, here we go. Let me pull this up here in Canvas. Come on. Close that one down. All right, we're getting there. All right. Fire up pie chart. My computer is sad. It's been running slow. I needed to reboot. I haven't had a chance. So hopefully you guys got Project 1 in. Our backtracking recursion. We got 11 submissions. I thought we might have some more than that. That's less than I had expected. Thanks. All right. I got my lunch here. I haven't even eaten yet. So let's take a peek. Okay, so we're going to build our maze solver. Calculate the shortest possible path. It will accept a 2D list as the maze, uses backtracking recursion. We should set something like a shortest path to get the shortest path step count, and then we're going to unit test so that we can actually find the shortest path. I think I said PyCharm, didn't I? It's probably already running. Just going slow. Might be going slow. I should be more patient. Not everyone has had a whole pot and a half of coffee. Let's see. We have PyCharm. Yep, PyCharm's trying. I can see it working there. It's going. It's going. Come on, PyCharm. There it goes. Maybe. No, that's not the one we want. Here we go. Start up a new project here. One maze solver. All right, here we go. Okay. Don't need anything to do with main right now. We'll come back to that later. I want maze solver, and we're going to make a class. Class maze solver. I'll have an init method, right, that takes a maze. So that takes a 2D maze. We'll set our self maze to the maze. Probably private is better, right? Because we don't want people changing it after the fact. Although if we're just copying a list, we should do like a copy of this, right? Import copy. Should do copy.deepcopy, right, of the maze, just to make sure we have a copy of it, not two references to the same location, right? I want to make sure we're doing that. Also, self is the instance value here that we're saving it as. So this way, all my other methods can get at it from here. So the maze is the argument that was passed to me. And then a couple different ways of doing this. I sort of liked this one. This is paths or step count, solution, step counts, and we did a list. I like that. That was fine. I hadn't done that before, but I thought that worked out to be a decent solution here. Right, and then we needed to find the starting location. So we're going to have a self dot current row is, I don't know, we'll start it at 0 for now, and a self dot current column is 0 for now. And then I'm just going to add a little helper method, find start here. So again, it could just be part of init, but this part, sure, make it a different method. Not a problem here. So I'm going to call self dot find start, just to separate out my concerns here a little bit. So I'm going to say for row index in range, the length of self maze, right? Because I need these indexes because I need to set the current row position to wherever that starting one is here. I'm going to say for column index in range, length of self maze. And now remember, they don't have to be square. so it should go off of the length of the row that I'm in. Right? There's no rule that said we had to have square mazes. So I'm going to check specifically the length of the row here. Hey, thanks for coming on by, math friends. It's I feel like I just saw you earlier. We have our amazing Professor Peter. Want to give yourself a shout out? That'd be awesome. Teaches Python labs in his calculus classes, and I'm like super jealous that we never did that when I was learning calculus, because I would have thought that was the coolest thing. Just amazing visualizations of things. Were you doing Riemann sums, I think, earlier? That was super cool. I'm thrilled, and I wish our math department here would change their math major so folks could take the Python programming course instead of our C++ programming course, because that would just make everyone so much happier, I feel like. Yeah, limits, that's right, limits. You saw we did our sequences and series a little bit where we were taking the sum of a geometric series, where r was between -1 and +1. I think you saw that and helped me out with it. So we do fun stuff too, but we're solving mazes here with backtracking recursion. Yeah, things are going well. Thanks for dropping on by, math nerds. I'm a proud nerd myself, so it's not an insult, don't worry. All right, so we're checking the row index and the column index. Column by the length of the row to make sure that we can deal with rectangles. And we're going to say if the self-maze at the row index, at the column index, is equal to, what do we say, like a start character? Sure, why not? Then we're going to set self.currentRow to the row index, and we'll set self.currentColumn to the column index. The other reason I like this is I can just return. I just stop, find start, and we're done. Right? Or we could even return, here we go. I like this even better. Let's return row index, column index. Right, we'll return that as a tuple. Right, remember, it's going to auto-pack that as a tuple for us. Sorry, it doesn't like the parentheses. So if we find start, return that as a tuple, and then we can say, hey, my current row, comma, this is the nonsense Python syntax that we get, is equal to self-defined start. So we'll unpack tuples for us automatically. Remember, I can say, hey, I've got two values. I'm expecting to get two things out of find start. Unpack that tuple and set them here. Now I've got a current row and current column. Right? Eventually, if we don't find a start, I'm going to raise a value error or something. Again, I didn't ask you guys to do this, but it's okay. This is just good habit. No start found. So if we don't return, we're going to raise an error. Bad stuff happened, crash. Right? Deal with it. Someone gave us a bad maze. But now, using the self-start, I can do like a return here, and I don't have to have a loop that breaks. And so I think this is a little bit cleaner of a format. Again, totally optional. It wasn't required to use a find start like that, but I think it makes things a little nicer for us. Okay? And then we're going to have our solve. Okay, this is our recursive solve. Remember, and we talked about our algorithm. Let me pull up my whiteboard here. Ooh, that's the wrong one. Clear that out. Okay, so we said, hey, we've got a maze here, right? Maybe we had a start. It doesn't have to be a very big maze. And we had some walls here, right? We had an end over here, and maybe some more walls. I don't know, sure, like that. We said we're going to do, what? Do you want to do up, down, left, and right? Sure, so we're going to say, okay, from wherever we are, can we go up? Can we go down? Can we go left? Can we go right? And we're going to recurse. Right, so at 0, 0 then, so we're solve at 0, 0, we're going to try up. No, we can't go up. So we're going to, let me slide this over a little bit here. We've got up, down, left, and right. So we can't go up. Let's try down. Okay, we can go down. So now we're going to solve at 1, 0, row 1, column 0. Right, we're going to try up, down, left, and right. Can we go up? No, we can't go up. Can we go down? Sure, let's go down. So now we're at solve 2, 0. We're going to go up, down, left, and right. We can't go up. Let's go down, right? So we're at solve 3, 0. Right? We're going to put our little breadcrumbs in here, sorry. 3, 0, solve, up, down, left, and right. We can't go up, we can't go down, we can't go left, we can't go right. This comes off the stack, right? And erase the breadcrumb. It's no good. Now we're back to 2, 0. We tried down, let's try left. So we can't go left, let's try right, okay? So now we're at solve of 2, 1. We're here. Put our breadcrumb down, we're going to try up, down, left, and right. Can't go up, can't go down, can't go left, let's try right. Okay, so now we're going to solve at 2, 2. Now we're here. Let's try up. Okay, up. Up, down, left, and right. So up says solve at so row goes -1, sorry, so 1, 2, with up, down, left, and right. Now we're here, put a breadcrumb. Okay, we're gonna go up again, we're gonna go up. So up, we're gonna go right, and then we undo, we undo, we undo. We're back to here, right, at solve at 2, 2. Those were all bad. We tried up, let's try down. All right, let's go down. Right, so now we're at solve 3, 2, and on and on and on. So that's the algorithm, right? After we exhaust all of our options here, we have to take out the breadcrumb. So we're going to say if I don't know what self dot can move to, we're going to take row index. So let's do this is up. Then we'll have a down. We'll have a left, and we'll have a right. So if we can move to self.row, so going up is current row -1, self.current column. Right? If we can move, let's go do it. Right? Oh, so solve, right? The first thing we had to do is put our breadcrumb down, right? So we'll put our breadcrumb down. So self.maze at self.current row at self.current column. Current column equals visited, right? I think I put a V in for visited. We've been there. Right? We marked the breadcrumb. This is breadcrumb. Okay. Then if we can move up, we're going to move up. So what we need to change then is current row needs to go down by 1. So we're going to subtract 1, and then we're going to recurse. Self.solve. Okay. If we come back from solve, right, we either hit a dead end or we did find the end and we're coming back. We need to undo this move. Right? This is the undo step. We're undoing. -1, there's the space. Right? So we just repeat this for each of the directions. Up, down, left, and right. So going down is row +1. So we add 1 to row, and then we undo it. We take away. Going to the left is column -1. So that's current column -1, +1 to undo. And right is current column +1. And then we'll take current column +1 and -1. Oops, too much. -1. Okay, if we've done all of that and we come back, let's undo our breadcrumb. Right? Because we're going to try each direction, and then we undo the breadcrumb. So we undo breadcrumb. We'll put it back to an open space. Just an empty space, sorry. Okay, that was our algorithm. What we're missing now is, hey, have we reached the end? Right, so if maze is equal to the ending space, right, we reach the end. Right, we win. Game over, but not game over, right, we're not done yet. So if we reach the end, great, we need to take our count here, our step count, we need to add to it. .append. Well, what are we going to append? Well, how many steps did it take? Oh, well, we forgot to track our steps. Right, so let's take a current steps, right, self.current steps, starts off at 0, and every time we move, current steps plus equals 1, take a step. Right, every time we call solve, let's take a step. So then we can append the current steps. So if we're doing current steps here, we need to undo that at the end, right? Self.current steps minus equals 1. Right, we're undoing the breadcrumb and the current steps. Right? If we're moving, great. That's a step. That's the breadcrumb. Count the step. I think we actually want to count it here. Because otherwise, the first time we call solve at start, it's going to count 1. So we want to actually report current steps before we count end as being 1. And if we reach the end, we're done, right? There's nothing else. So we want to only do these other things, right, if we didn't reach the end. So if we reach the end, we're done. Don't do anything else. Otherwise, try all the moving. Mark it as visited, right? Because we don't want to visit the ending square. Count your steps. Do all your move up, down, left, rights. Okay, we good so far? Right, so then we need, well, hey, how can I go somewhere, right? This is the if can move. We're going to define can move. That's our little helper method. Let's put it, I don't know, up above, down below, doesn't matter. We'll do it here. Define can move. takes a row index and a column index. Okay, well, we need to check, is the row within bounds? Is the column within bounds? And is it an open space? Right, so we're going to return 0 is less than or equal to row index is less than length of self maze. Right, that's 1. That has to be true. And same thing for column index. Oh, that tabbed in really funny, sorry. And column index is less than the length of self maze at the row index, right? Check the row because it's a rectangle, or could be a rectangle, right? And so they're within range. And remember, when we and, the first time we find a false, the whole thing's false because Python's smart. It doesn't need to waste time calculating other falses or trues if it knows the whole thing's false. So if the row is invalid, we're never going to check the column length because the row is invalid. Otherwise, it would crash. And then self maze. So if they're both good, I can check my maze at row index, at column index is equal to an open space. Now, you might be noticing, and you probably ran into this yourself if you went this route, that this means you can never land on the end. So all of this needs to be an or it's an ending space. Right? So I can either go to an open space or an ending space. Okay? Oh, it doesn't like the extra spaces there. Don't need that. Why is it unhappy now? Continuation line. Okay, sure. I want them all indented at the same level, I think. Why is it unhappy? Under indented for visual indent. Okay, sure. Oh, because it was in parentheses. Why not? Okay, so we're saying, hey, if the row is valid, if the column is valid, and it's open or empty, or the end, I can move there. Right? And I'll recurse. I'm going to try it. And if I reach the end, add the step count. Great, that's it. We're done. Now what we need to do then, we'll have a method for define shortest path. Right, we're just going to return the minimum of self.step counts. Right, whatever the smallest value is in there must be the shortest path. Okay, how's that look? And maybe I'll move that one. Oh, that's fine. Should we try it? So now let's actually try and build a maze. Right, so I've got that maze. I'm just going to cheat here because I've got it copied over here. There we go. And we need to import or from maze solver, import maze solver. Right, here's the maze. This is the example one I posted in the class Discord channel. Let's see if it solves, and then we will. Oh, we didn't do the print statement, right? I forgot to do a print. So that one's not very interesting. I think I gave you most of that one. Maze solver. It's a. Oh, I added. We don't need that one. I'd added in some like printing to tell you the number of steps. Okay. So we're going to join all the rows as a string. Oops. For row and self maze, self under maze. Right. Join them together as the string version with new lines. It's like exactly like we did in nCleans. Right. It's just stealing that. So I can print the maze. Right. So for fun, if we solved it. Excuse me, let's print ourselves. So this will print a solution, right, when we solve it. And again, this is just for fun, just so we can see that it's being solved here. And then we're going to print maze solver dot shortest path. Right, we expect it to be 8 steps, right? 1 step, 2 steps, 3 steps, 4, 5, 6, 7, 8 steps to the end is what we expect to get back out. Let's run it. See what we get. So let me zoom in a little bit. So here's one solution, right? Here's another solution. Here's another solution. 8 steps. Feeling pretty good. So now the next step, then, what I asked you guys to do, right, was to write unit tests. Let's come back over to maze solver. And really, the only thing we're testing is, does solve work and give me back the right shortest path? That's really it. Okay, that's what we're unit testing. So let's, oh, I don't need those parentheses, right? There, now is it happy? Okay, now it's happy. So let's go to test. I don't have any tests. Let's make some new tests. Test solve, sure. Okay, so we're gonna do that AAA format. We're gonna arrange, we're gonna act, we're gonna assert. So I'm gonna, instead of doing all this in main and having to look here, right, I can do it over here. So arrange, I want a maze. I want to act, I'm gonna create a maze solver. Maze, oh, I gotta import here, sorry. So let me steal that import line. Okay, so maze solver, maze solver, no, maze solver equals maze solver given the maze. And then we'll have an expected number of steps here as well, right? So an expected shortest path is 8. Actual shortest path is my maze solver. Dot solve. Oops, sorry, we gotta solve first. Then maze solver dot get shortest path. Then we can assert. We'll assert equals self dot assert equals my expected shortest path and the actual shortest path. That's one unit test. Okay, and let's change it around a little bit. Shortest path. This is other maze. I'm just going to put end over here and start over here. Sure. Let's do another one here. Let's change it up a little bit. So if I were to move the ending space here then to here, right, it should be 7 steps. I should get 1, 2, 3, 4, 5, 6, 7 steps and have other ones as well. Right, so now the shortest path to be 7. Just come up with some different ones, right? We would probably want to test that we could do a rectangle. Right? Testing other maze. I have too many other mazes. Other maze 2. I don't know. I'm running out of good names for this. Solve rectangle. Right, so we just put in some new spaces. Right, why not? We should get the same solution, right? But it will have extra spaces. Should still be 7 as the shortest path. All right, so let's run our tests. Solve rectangle worked. Oh, I want to run all, sorry. So let's go back up to the top. Why is it complaining? Not enough spaces. Is that better? There. Let's run them all. Yeah, all right, they worked. And again, we see some printouts, so that's fine, but we see all the possible solutions. So there's a bunch of them for this bigger maze, right, where it visits a whole bunch of other spaces, takes a bunch of funny paths. So another one, just for fun, let's do this. Let's solve no walls. We don't have any walls. Right, we can see the backtracking is going to get a little crazy here. Right, it's never going to get super deep in recursion. Like the maximum depth is the maximum number of spaces. So this is a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So at most we're going to have 25 depth in recursion. Right, if it takes the longest path possible, like down, up, like if it snakes around perfectly, we'll get 25. But it has to try every single combination. So if I go down first and then I go right, or if I go down and then I go down and then I go right. So this one's going to take a little bit longer here, but it's still going to work. Right, this solve no walls, notice all these prints it's doing. So prints are actually really slow. So if I were to stop that, right, the print is actually the slow part here. So let's comment that out here. And let's run this one again here. Right, shortest path was still 8, right? But it took a little while. It took over a second for that one to run. Right, so the backtracking is just going to find them all. It should work. Right, so how's this one feel for you guys? You doing okay? I got lots of questions, lots of last-minute questions, which in general is not ideal, right? We're going to have 2 weeks for every project, longer for the final project. And if you wait until the night before it's due to ask me questions and wonder why it's not working, the odds are it won't go well. Right? I'm not always up till 1 in the morning, 1:30 in the morning answering emails or whatever. So just please plan ahead. Ask questions early. Get started early on things. And we can go from there. Does that sound okay? All right, you guys are relatively quiet. Let me do a quick poll here. So let's say project 1 did terrible, did okay, I aced it. Just tell me what you think. They're in the Twitch chat. There should be a little poll at the top. It is anonymous, right? Just let me know how you feel, how you think about it. No, this is just backtracking recursion. The left hand always touches the walls different. That's a fun way to solve mazes too, non-dairy. We're just looking at backtracking recursion here. Okay, and I'll post all that out in my GitHub so you guys can see it. It's no big deal. 2001. Let's find the right course here. Go, and project 1. Here we got the maze solver. We got some tests. Life is good. Yeah, thanks, non-dairy. I appreciate you using that Nightbot link. Last time I had a great idea of adding it, and I went to Nightbot to my config and realized I had already added a command for GitHub. So that's, that's good. All right, so 3 people said they aced it. 2 people said they did okay. No one said they did terrible. All right, that's not too bad. 5 people answered the question. That's all right. Not too shabby. All right. So we ready for new stuff? Or questions about this one before we move on to new stuff? Again, lots of different ways of doing step counts. You could keep... so someone actually had a clever idea I liked. Instead of having to count steps and add and subtract every time, when they reached the end, they just counted the number of breadcrumbs. Right? So as many breadcrumbs were in your maze is how many steps it took. I think you had to add 1, though, right? Because you had to count landing on the end. But essentially, it got the right thing. Right? So that was kind of a fun way. So I like just tracking it here. That's one way to go about it. You got some information there. Solve could have taken a row and column, but that makes it harder for someone using the maze to call the function. Remember when we looked at recursive functions, you want to make the public function super easy to use. Right? If you want to have a private recursive function that takes a row and column, that's a cleaner way to solve it. So if you did solve it that way, it's okay. You're not going to lose points, but just know it's not a clean solution. Because then whoever's telling me to solve the maze has to tell me where to start. And really, we should just be able to go start anywhere we find an S. Right? That sort of idea there. Okay? All right, why don't we take a quick 5-minute break, and then we'll come back with stacks and queues. I have not had a chance to grab lunch yet, so I'm going to snack on my cheese and crackers real quick. We can go from there. Well, so we track every single possible route, Eric, and then to find the shortest one, we just count the minimum. So every time we find a solution, we're going to log it in that list of step counts. Another way of going about that, if you didn't use the list, you could have had like self.shortest possible path. And if the new path was shorter than that, we could change it. We could go about it that direction if we wanted to track like self.shortest path. You'd have to start at something ridiculously large, right? But then your idea would be, if we reach the end, if self.current steps is less than self.shortest path, right? Self.shortest path is equal to the current steps. So you could do something like this, where you just keep finding the lowest value and only tracking the lowest, right? Or track this way. Go add step count list, find the min later. So this is probably less memory efficient, keeping the list, because then if I had 50 solutions, I have to keep 50 numbers around. I'm not too concerned about that at this point, right, in terms of efficiency. So like backtracking is not the most efficient solution. It's definitely terribly slow, and there are better ways to solve, right? But this is one approach, and it's just a fun way of looking at recursion, I think, because it does all this loop stuff for us. And remember, our rule is anything that can be done recursively can be done iteratively. So there's ways to write this iteratively where you have to track what your location is and what you're doing inside of a loop. It's confusing, right? And this is much more straightforward because what we're doing is we're using solve as that loop itself, and solve is tracking its current row and current column. So like a lot of the solutions you'll find online keep a list of moves, and they just add and subtract from that list of moves, and it's nonsensical. It works, and it's okay, but that's how I know when people copy paste stuff from online, because no one thinks like that, right? It's the hard way. Okay, so we'll take a quick break, and we'll come back in 5 minutes or so. We can go from there. We put some music back on. Do you guys like alternative metal or heavy metal, sort of like the loud rock style? I don't know. I'll always play this one. I've got a friend in the band, and I've started playing his music, but it's a little heavy. Let's see. We'll come back here. You want the metal? All right, we'll do the metal. You got it. You got it. Hang on, let me find it here. SoundCloud. All right, I will flip this over here then. That's that one. Here we go. All right, it's a little loud and aggressive, but it'd be okay. LT, I don't know what LT is non-dairy, I'm sorry. I'm a little slow. All right, let's give this a shot. Come on, hit play. It's loading. There it goes. All right, gang. I think we're back. Let me find where that is. All right, it's always fun to try other things. So, there's our maze solver. Yeah, just a quick break. Trying to be a little shorter than last time. We have less time on Python days. We only have hour 15 blocks. All right, so let's start up stacks and queues. Stacks and queues are fun. They're like a specialty data type, data structure that have specific ways of interacting with them, which is fun. Excuse me. Zoom that a little bit. So the rule with a stack is you're probably familiar with, right? So we have a stack is we'll call first in, last out, or FILO, or last in, first out. Most people say first in, last out. And then a queue is first in, first out. Right? So we have FILO or FIFO. Or some people say last out, first in. Or no. No, sorry. Last in, first out. LIFO. That's right. Last in, first out, or first in, last out. Ugh. First. Right. LIFO. Yeah. Sure. I think, sure. Whatever you want to call them. It's okay. So they do it with the stack, right? You put something on, or you put something on top, you put something on top, you put something on top. The only thing you want to take off is the thing that's on top of the stack, right? Otherwise, you'd knock the whole thing over and it's just invalid. Low, yeah, probably not low. Last out, first in. I don't know. Nobody says that, I'm sure. But I've heard some weird things. Someone argued with me one time because one of the quiz questions was, hey, a stack is a last in, first out data structure. And they answered false and said, no, it's a last out, first in, or something like that. It's like, yeah, I mean, okay, but okay, whatever. Like I initially marked it wrong because they said false to it. Like I didn't even look at what they said. They're like, no, I said the right thing. It's like, well, that's just backwards, but okay, it worked. So what we do is we can implement these things with different structures. Okay, so if we have a class for stack, we're going to define an init method of self, and what we're going to do is we're going to have a self internal data storage. It's just a list, right? We're going to abuse this Python list all sorts of ways, right? Because it's already done for us. We don't have to reinvent the wheel here. Okay, so we're going to self data, and then what we have is you have methods. You have a push method. You push something onto the stack. We'll take self data and we will append the item. And then you have a peek option. And peek shows you the thing on the top of the stack, but doesn't take it off. So we're going to return self data at index of length of self data. Self.data -1. Right, remember, the length of items that we have is total number. -1 will give me the last index. And actually, we should also check here, right? If the length of self.data, if that's 0, we're going to raise a value error. Error, and say stack is empty. No good, we're empty. We can't do that. Otherwise, we can give you something, sure. Okay. And then we'll have a pop. Pop is going to return that last value. So instead of peeking, we're going to actually take that value back off. And turns out stack already, or a list already has that. If you call pop, it gives you the last thing. I'm going to be explicit here and still do the same thing. I know we don't have to, but just to show you, right, hey, we're taking off that last index. Right? And that will remove it from the internal data storage. So if you remember anything about the performance of lists, remember we spent a lot of time in lab looking at this. Adding something to the end of the list, on average, takes how much time? We're talking about average time, not worst case. We know worst case we have to resize and then add it, and we'll take n operations. But average time, when we do our amortized average, or whatever we want to call it, our fancy term, right? O of 1, right? It's constant. It takes one operation. Again, on average, because we've averaged out all those copies. To look at something at the top of the stack, to get something out of a list is constant time, right? If you have an index, we can read it like that, constant operation. To take something off the end of a stack, specifically the end, is also a constant time operation. Right? So if we look at this, these are, we could say O of 1. Is that an O? I forget. Oh, they always look like zeros to me. O of 1 and O of 1. Right? Could take something off the last piece of the stack, on average, is 1. Right? When we removed a bunch, eventually we get that halving where we have to resize ourselves. So the worst case is it has to resize. But on average, it's a 1 operation because it takes the last thing and nothing has to shift into place. Now, if we were to take off the front of the stack, we'd be O of n because we'd have to shift n items, right? Or if we were to insert to the front of the stack, we'd have to take off n items, or bump n items down after adding it in here. So this is good performance with the stack, right? But we have very limited access to these things. So we're trading off performance for access. And again, we could do all of this stuff with the Python list. The reason why we might make a stack class is to protect ourselves from doing bad things like, oh, hey, it's a list, I can insert in the middle. Oh, hey, it's a list, I can look at all the other values. If your problem can be modeled with a stack, you might want to use a stack, right? Because if that's what your problem definition is, if whatever you're interacting with behaves like a stack, put the data in the stack then, so that way you can only do the stack operations. So our assignment, our next project, will be doing something with stacks and queues. And that's just how we're going to treat them, because this is how we're going to interact with these things as if it were real life. Right? Just trying to say, if this is the real life behavior, let's force ourselves to only use this. So really it's just a wrapper around list. Right? This is just a wrapper around list. Just to prevent other access. Okay, so that's a stack. That's all there is to it. This one's really quick and easy. Okay? Excuse me. You okay with stack? Again, this was like a 5-minute thing. Not too complicated. This one's pretty easy. The queue is a little bit harder. We'll talk about queue in a second. All right, sorry. These dried seaweed things are amazing. So because data is private, the only way people interact with us are through our public methods. They can only push data on, they can peek at data, and they can pop data off. So we're only allowing them to get at the top of the stack ever, right? Whether or not they're adding something to the top or taking something off the top. That's it. Because if it was just a list, right? If we were just used a list itself, we can call list insert, we can call list remove, we can call list anything, right? Anything that list can do would be accessible. So if we use the stack class here, we're restricting them to only our public functions. Saying this is how you interact with us. This is the abstract way which you interact with my class. So like I could let's make a stack. My stack equals a stack, and I don't know, for number in range 10. Let's take my stack. Stack dot push the number, and then oh, actually we should add one more here. We can let's add a length here. We're just going to return length of self data. Okay, this way we can use it in a loop a little bit more easily. Right, we can say then while the length of my stack is greater than 0, let's print my stack.pop. Right, take the value off, throw it back on top. Right, so add a bunch of numbers and then pop them off. So what we're going to get is reversed order. Right, we put them in, they go in, 0 goes in first, and then 1, and then 2, and then 3, on and on and on. 9's on top. And then we pop them off, we get the top value. Pop them off, pop them off, pop them off, pop them off. So it's not a quick way, but it's a way you could reverse things if you wanted. Throw it in a stack, pull it back off. I don't recommend it, but it's one way. Right? Those are kind of like the silly, nonsensical interview questions. Like, if you only had a stack, how could you reverse something? Or whatever. Or how could you reverse something if... Yeah, sure. We could do that. Right? So, but now with my stack, the only things I can do are push, pop, and peek. Right? Versus if I had a list, like my list here equals a list, and we could do this exact same thing here. my list, now it's append, right? And my list pop is still the same, works the same, right? We do the same thing. It's going to act exactly the same, but now if I wanted to, I could also do other things in the middle here. I could take like my list insert at 0, insert 42, right? And now all of a sudden you have a 42 in there when we shouldn't have been able to put something on the bottom of a stack, right? So if it should be a stack and you should only be able to pop, push, and peek, make it a stack, right? If you can do other things, use the list. Go for it. Okay? That's a stack. Now, the queue is a little bit trickier. So let's write the class for queue here. Class queue, right, is first in, first out. So again, we're going to do this with an internal data storage. Self-data. Okay? We could do that. Now, if we want to, so queue has enqueue and dequeue, and front is typically what we'd call those. So you could enqueue an item, and enqueuing an item adds it to the queue. So that's self-data dot append, right? When you get in line, you go to the back of the line. Define dequeue. We're going to give you back the last thing. And again, we're going to check here because might as well if we don't want to dequeue something. If we're empty, we can't. Otherwise, we're going to return self-data.pop at 0. Take the 0th index item thing in front and pop it. Right, and then we could define we usually call it front. Return self.data at 0. Now, give me the front thing. Again, probably also check. Okay, so average performance here, O of n, or O of what? O of what for enqueuing? Adding something to the back, we already talked about, is O of 1. Right, looking at an item, sure, O of 1, right, constant. I can peek at the front thing. I can give you the front thing, no problem. Dequeuing here is our problem, right? This is O of, if I have to take the thing out of the front, everything else has to shift back into place. That's O of n. Right? The more n I have, the more shifting I have to do to take something out of the front. I'm going to call this a dumb queue, right? Because this is a dumb implementation. We can do better. But does that part make sense? Like the basic implementation is first in, first out. You get queued at the end, you get taken off from the front. Right? When you dequeue something, you come off the front. But now we have this performance problem. Is a problem. This is not efficient. That's not what we want. Right? And if we said, oh, well, what if we wanted to dequeue really fast? What if we just put ourselves at the end? Right? If we added to the front and took off the end, well, dequeuing would be fast, but enqueuing would be slow. Right? Inserting to the front would be slow, and dequeuing would be fast. So we can't just even flip it. Right? That still doesn't work for us. Right? So we have to do something better. Okay? Now before I get to the better thing, is this making sense? Because the better thing is crazy. But I promise it makes a lot of sense once you wrap your head around it. The better approach here is really good. We pause for a second. I'm going to eat some seaweed while you think and chat. I just feel like a duck or something when I'm eating seaweed. You just like suck it in your mouth. I'm sorry, you don't need to watch that. My apologies. All right, so let's clear this out. So with a list, right, we get some spots for data. Boom, 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 boom. Okay. When we add data, we're adding from the back, and we take data off, we take from the front. So if we wanted to be faster, we could be faster. So let's look at, I'm going to copy this here. This is a faster dumb queue. Okay, so the faster dumb queue then, we're going to keep adding to the end, but now what we're also going to track is a self.front index. So actually it starts off like -1. Sure, why not? And every time we, oh no, here we go. This starts at 0. So every time we dequeue something, we're going to dequeue from the front index. So this is our item. And then I'm going to take my index and I'm going to increase it by 1. I'm going to return the item. So when I peek at the front value, then I need to show them what's at my front index. Okay, so the idea here then is if I add a bunch of numbers, right? If I added like, I don't know, let's just do the alphabet, right? If I added A, B, C, D, and E. Okay, if I haven't popped anything off, my front index is 0. So this is front is 0. When you ask for the front, I take this off. Right? And actually, no, I'm sorry, we don't pop it. We just take it here. That's right, we don't pop. We're going to just get the value here. Okay? Get the value, return it. We're going to leave it there. So actually what we're going to do is after we take it, we're going to assign it none. Remember, none lets the garbage collection free up afterwards. If there's no reference to something, no variable pointed at it, saving it, storing it, it can get garbage collected. So we're going to take the item off, and we're going to put none in its place, increase our index, and give you back the item. Hydration. Thank you so much, gluten-free. Gotta have your coffee. You know, the smart people, who I do believe, say it's not hydrating because it's a diuretic, but I'm going to drink my coffee because I'm not giving up coffee. You just have to alternate coffee with water, right? Okay, so now what we get is dequeue is constant time. Right? We're going to take the thing that was in front and give it to you. Now we also now have a problem though, right? If we can't just check if length is not 0 anymore, right? If our length, oh, a stretch, thank you. Oh, there we go. And sitting in this chair all day long is rough. I do miss walking around campus. We had a really pretty campus, or have a really pretty campus. It's a shame. You know, we'll get back to normal soon. We'll get back to normal, but we'll get there. So now I also have a problem if the length is 0 or my self.front index is equal to the length of self.data. Right? So as I pop these off, right, if I add 5 things, my length is 5, right? Front index is 0, and then front index becomes 1, and then becomes 2, then becomes 3, becomes 4, right? After I pop off the 4th item, or return the 4th item, I'm going to increase front index to 5, but there's nothing here. Right? Now you see the problem with this, though, we put a bunch of nuns in this place, is that the list is never going to resize. Yes, posture, thank you. I need that. So I've got this really cool backboard, which is nice. Just put behind you. Make sure you can't slouch. I mean, I guess you can still kind of slouch on it, but it's made to like keep your lower back kind of popped up a little bit. So thank you. Thank you for that. Right, so now our problem, what's wrong with this one, is faster, but never resizes the internal list storage. So our list internally, this data here is never going to shrink. It's just going to get bigger and bigger and bigger and bigger and bigger forever because we never free up the memory. Right? Eventually, like with our dumb one here, if we enqueue 1,000 things and then we dequeue 1,000 things, the Python list is going to shrink. Remember we looked at the size in our lab? Eventually it does the halving, just like the opposite of doing the doubling. It will shrink itself so it doesn't use too much memory. So this is faster, but still dumb because it's using too much memory. So in this case, we get constant time performance though, right? We're just getting something by index and returning it. Sure, O of what? It's 3 operations here, but remember we throw away coefficients, we still say it's O of 1, it's constant. Okay, and the front, sure, still there. We also want to do this, right? Or a front index is the length of data. Q is empty. Okay, so let's see if we can use it. So we did all these things here. Let's do it. Let's do some more. So we'll say my Q equals a Q. Let's do the faster dumb Q. right? And then for n in range, or number in range, let's go 10 items again. Let's take my q dot, and we're going to nq the number. And this one, it should also have a length, right? We should do the same length thing. Okay, we have a length. And we can say while the length of my q is greater than 0, let's print my q dot dq. Right, take the thing off the front. Let's see what we get. Ooh, uh-oh, q is empty. Well, something went wrong with our logic here when we dequeued. Front index, is that moving up too fast? It equals the length of self-data. Should have worked. Okay, so what is happening here? What is happening? It should be 0, right? We start at 0. That's the 0th thing. We dequeue it. We add 1. We return the item. So we got all. Yep. So our length function is bad. My mistake. So length of self-data, because we're never resizing, is wrong. So we need the length of self-data minus the self-front index. Right? As many items as we have in front, we need to, or we don't have in front now, we're discounting from our length. There we go. That was the problem. The length was bad. Okay. Self, yeah, as this in other languages. It's self in Python. All right, there we go. So now we get out our values and we don't stop, or we do stop properly when our length becomes 0, because we're accounting for the dead length in front. Right? This is all dead space. We pretend it doesn't exist. Okay? We all right so far? Now, could we do better? Can we do better than the faster dumb queue and not use too much memory? Yes, we can. We sure can. I'm glad you asked. I'm glad you asked. You guys are so smart to know that we could do better. You must have been reading in the book, because you guys do that, right? We have a textbook. It's not just there as a paperweight. Although my old calculus book is now the monitor stand for my second monitor to keep it up a little higher than my laptop screen. I'm hoping to eventually give it to my son. He's interested in higher order mathematics, but he's not quite ready for calculus or even like the pre-calculus chapters yet. He's still only in 7th grade, so there's not a big rush. But he wants to get there because he thought it was cool that I was learning calculus. And calculus is just amazing. It really is. Like, there's some super cool stuff that we have figured out how to do. It's crazy. So read your book, right? Read your book. That's the moral of the story. Right? I'm going to give you the highlights. I'm going to give you examples. I'm going to try and pull out the interesting stuff. You still got to read the book, right? Because honestly, like, it's a college class. I think you guys are familiar with the idea. The more you put into it, the more you're going to get out of it. Right? Like most things in life, right? If you're putting the energy in, you're going to get more out of it, right? If you're spending time studying, if you're spending time reading, spending time practicing, doing the labs, you're going to get better. If you just show up and watch me occasionally, you try and watch the VODs every now and then, and you're falling behind, but you put a little bit of time into it, you might scrape along, but you're not going to get very much out of it, right? You're just going to get the bare minimum out because you put the bare minimum in, right? That's a pretty good rule, right? The more you put into it, the more you're going to get out, okay? So please do read the book. That's why we have the quizzes every week, right? To encourage you to read the book, right? 10% of your grade comes from, like, can I open the book and find the answer? Like, they're not hard quizzes, right? I promise. Like, all of it should be able to come from the book and nonsense that I've said. Not nonsense, the stuff that I've talked about in lecture time. You should be able to answer all the quizzes, right? And there's no time limit. So that there really should be no reason you can't get 100% on all the quizzes and get 10% of your grade locked up in the bag. Done. Right? You'll get 10% of your grade from doing the labs. I go over the answers to the labs, but if you're just waiting for me to give you the answer and you copy paste a bunch of crap and you don't understand what happened, you're not going to get very much out of it. if you're practicing the labs, trying the labs, working on the labs, struggling through making it work, you're going to get more out of the labs and get 10% more of your grade. Okay? Sorry, that's my soapbox. I'll get off the soapbox now. So we can do better, though, right, than our faster dumb Q. Right? So we're going to try this one more time here. I'm going to post a quiz for this chapter later today. It'll be due in about a week or so. So I'll try and remember to post them on Thursdays after class, and then they'll be due usually a week. I think I've been moving them out till Friday, just to give you guys a little extra time there, because sometimes I don't post them right away. Let's see. We've got quizzes here. I've got to grade a bunch of stuff. Thanks for turning stuff in, folks. Yeah, so I'll post the Chapter 6 quiz. So this one's Chapter 5 is due Friday, tomorrow, 11:59 p.m. It was missing a question. I hit the save button apparently too soon, or didn't hit the save button or something. I don't know what happened. So that was only worth 8 points. Sorry about that. There should have been another question, but if I add it now, you won't see it, so don't worry about it. Not a big deal. But I'll post the Chapter 6 quiz later. It'll be due next Friday, 11:59 p.m. We'll just kind of follow that format. Every time we cover a chapter, we'll post the quiz on Thursday. Yeah, sure. I mean, I can make it Saturday or Sunday if you guys really want the extra time, but I found the more I move deadlines out, the more people just wait to the last minute anyway. So, like, if someone says, oh, well, I can't do it Friday, can we do Saturday? I'll say, sure. And then some people are like, oh, well, I can't do it Saturday. Could I do it Sunday? And in my head, I'm thinking, well, it used to be due Friday. Like, why is Saturday not good? Because, I don't know, that sort of thing. That's just my personal complaints about trying to move deadlines for things. So I don't go over the answers to the quizzes in class. When we meet in person, I usually would. But I haven't done that online. If you're curious about any of them, please do let me know. I'm happy to talk through them with you guys or go over answers in class. I can do any of that. But not going over the answers gives me a little bit more flexibility. If someone says, oh, I just forgot about the quiz, or things were busy, this week sucked because COVID, whatever, right? I can say, oh, sure, turn it in late because I haven't told you the answers yet. But like with the projects, once I go over a solution, I can't take that late. So the labs I can take late if needed. The quizzes I can take late if needed. But please ask me ahead of time. Don't just assume that I'll take it late and turn it in late. Right? The syllabus has my policy, and I do a decent job of sticking to that. That I don't accept late work unless you have prior permission. Right? And that is in the syllabus. My mask? Oh, it's out in the car. I leave it in the car for any time I go places. Come on. Load the syllabus. Let's go, Canvas. Let's go. I think it's in here. I just want to sure, I'm proving a point. Why not? Without prior written approval. That's an email. That's a text. That's Discord. Any of those are fine. I try not to do anything over voice because I'm going to forget that I said it. So if you've got it in written form that I emailed you or I Discord messaged you or texted you, right, we can pull back up that history. But if I just say something, I'm going to forget. Let's be honest. Right? I've got a lot going on. I'm not going to pretend. So written approval for projects and homework. It's almost never for projects, but homeworks and labs and quizzes, right, those sorts of things. If something comes up, let me know ahead of time and I can work with you. Okay? All right, so can we do better than the faster dumb Q? I'm going to show you how it works, and then that will be our lab exercise. We're actually going to try and implement the faster Q. So it's a fun exercise. So let me clear this out here. Okay, so imagine we had this list, right? And let's add A, B, C, D, and E to it. Okay, so that's our list. And then we take off A, we put a none in here. We take off B, we put a none in here, and then we'll add F and G. Sure, we can keep doing that, right? Why not? Whatever our list size happens to be, okay? Once I run out of space here, right? So what we need to do is we need to have additional space in the list. We can manage it different ways too, but typically we could go, we can just let list do its thing. So if there's not space in list, we can just do this thing called a circular. So this is a circular queue. Circular queue. So let me do that. So I'm going to undo. So we did A, B, C, D, E, and we took off A and B. Now when I'm going to go add something, I'm going to say, hey, do I have any free space here? Well, yeah, I have free space because my free space is over here. So I can add F and G over here. Right, so this is still my front, right? I'm tracking front. I need to also track the end. So, okay, before I did F and G, right? I'm tracking front and I'm tracking end. So end, END, is here. So if I go and add something and I'm at the end equals, right, the length, then I need to say, hey, do I have any more space in the front? Do I have any room to the front? If I have, we just popped them off or DQ'd them. We just took them off. So if I have space in the front, right, I'm going to use it. So I'm going to put F here and G here, right? So now this is the end of the queue, end of the queue, okay? So end is no longer the length, right? If it's the length, then we circle back. Now we have the end. So if end meets the front, well, I need to resize. I need to get a bigger queue to add something, a bigger list, and then I'll copy it in C, D, E, F, G, and put in the new thing, right? We'll put in, say, H, okay? And I have to reset front and back. So now front comes to here, back goes to here. If I pop off a couple more things, right, let's take the C and the D and the E. Now front is over here at F, and I have 3 blank spaces. I can add some more stuff. So typically what we do is we would go through that resizing process ourselves, like when we did our own silly list, we would do the doubling. We could do that as well. So we could track, so much open space. We might say, hey, a queue is going to be 10 spaces big to start, right? And if we run out of space, then I can double. I'll make a new list of size 20 and do the copying steps. So that's a circular queue. We're going to build that in lab. That'll be our lab exercise to write our own circular queue. So it's a little bit more complicated, but what it lets us do is it solves the memory problem. Because I'm never going to be more than a factor of twice as big, right, than the number of items that I store. Because as we start taking items off, we can resize. It's a little bit tricky with doing that because the Python list won't resize it automatically. We can add in some additional things if we want to resize ourselves. And we'll look at all of those options. But we'll keep blank. So the idea is we keep blank space in here, just like we did with our other list, right? When we kept some blank space in there. So we had 2001 winter. I think we did that with our list, right? We kept some blank space there. That was dynamic array ripoff. Yep, that was it. In chapter 5. Right? We said, hey, check and resize. If we don't have room, let me zoom that a little bit for you. Right? Go ahead and double. Make a new list, copy over. So we've done this sort of operation. Oh, nice. Yeah, it's an IKEA loft bed that my son outgrew. He got tired of hitting his head when he'd wake up in the morning and sit up. So when we did the reshuffling of rooms, I claimed it for the office because it's got a nice desk in it. And then the bed is just storage, essentially. I can just store things up here, which is nice. And then I've got my games and stuff back there. I just had to buy another shelf for games. I'm super excited. We have outgrown the IKEA 2x4 storage unit full of games, and we're adding more board games. So it's lots of fun. And so we've done this check and resize. We've done the reorder, move them. So we're going to combine those sorts of things to make a circular queue, which will solve all of our problems. So the indexing, right? So we need to track where the front is. So the front is the next item. So like we were tracking front in here, with our faster queue, we had the front index, right? And every time we dequeued something, we moved it up by 1. So we do need to have a little bit of extra logic, right? Because we need to be careful that once we've dequeued C, D, and E, right now front needs, once it hits the end, it has to go back to the beginning. So there's a couple ways of doing that. A lot of that is with modulus. Right, the % sign. Modulus does a whole lot of cool things for us, and we're going to take a look at. And we'll do that in lab. Build the circular queue so we can get O of 1 performance for N queuing, O of 1 performance for D queuing, O of 1 performance for looking at the front thing, and it's not going to just infinitely grow memory over and over and over and over. We solve the memory problem. Okay, that's what we're going to do with the circular queue in lab. I got 4:45. It's been fun. If you guys got any questions, let me know. Oh, we haven't talked about the next project. Shoot. I will post the next project for you guys, and it's relatively self-explanatory, but it might be you gluten-free. I don't know. Is it? Oh, it's staticky. I'm sorry. I must have done something wrong. Maybe I bumped the wrong thing. But we're out of time. I'm going to post the assignment, and then we can talk about it again on Tuesday if you have questions about the assignment. Okay? All right, you guys take care. Let's see. Is there anyone else around on Twitch we can go pester? See if there's anyone around. You can go learn some good stuff. Check out the Knowledge Fellowship, friends. Let's see. Shout out for the Knowledge Fellowship there, TKF. They're a bunch of cool people. We already dropped in on Dr. Mick, right? Have we checked out Dr. Young's lab yet? You check out Dr. Young. He's awesome. Let's pull up his stream and head over that way. We'll learn some chemistry. All right, folks. I'll see you around. We'll be back on Monday for lab. I'll post the assignment. If you got questions, I'll be hanging out in Discord, and we go from there. All right, you guys take care. See ya.